Hi, my name is Anthea Chung, and I will be talking about my paper on improved student model training for acoustic event detection models. This work was done with Qingming Chang, Chichi Kao, Ming Sun, and Chao Wang from Amazon Alexa. So the brief introduction of this paper, we're focused on acoustic event detection, or AED, which is the task of predicting sound events and their time boundaries. And this is a difficult task compared to audio tagging because it is hard to obtain high quality annotated clips which contain labels of the onset and offset times. There are many practical applications of this task, including media indexing, surveillance, and smart home devices' abilities to interpret acoustic events. And one thing about this task is that the state-of-the-art models are usually ensembles comprised of multiple layers of convolutional layers or contain custom architecture. So our goal was to apply knowledge distillation techniques so that the performance from high quality teacher models, which might be ensembles or have multiple layers, can be translated to a simple student model. And the techniques we used included curriculum learning, the custom spec augmentation method, and loss masking. Applying these techniques, we obtained a strong event-based F1 score of 42.7%. And this is a jump to 34.7% when training with the vanilla KD method. This performance also matches the top submission of the 2019 Task Force Challenge. Our data set has 10 different event types and includes weakly labeled clips, which only have event labels, strongly labeled clips, which are synthetic and contain the onset and offset times for each event, and a large set of unlabeled training clips. Our model was a top performing submission from Lin et al. It's an ensemble of 6 CNN models, which we use as a black box to generate pseudo labels for our unlabeled data set. And our student model is a 3-layer LSTM model. It outputs the frame level or strong predictions with a fully connected layer after the LSTM layers. And we use an attention pooling mechanism to obtain the clip level predictions. So for the model training overview, what we do is we take our data set and apply curriculum learning to obtain a scheme of samples that we gradually introduce to training the student model. For each of the inputs, we also apply our custom spec aug data augmentation method. And we use the teacher and the student predictions, which contain the clip level and the frame level strong predictions. For the clip level predictions, we use that to calculate the weak loss, while for the strongly labeled predictions, we apply a mask and then send it to the strong loss. For the curriculum learning, the basic idea is that we gradually introduce different samples from the unlabeled data set to training. Each generation is 5 epochs long, and we rank the difficulty of each sample using the simple heuristic, which is the maximum difference between the teacher and student scores across all classes. In the easier first scheme, we add the bottom 20% scored samples first, and then the bottom 40%. And in the harder samples first scheme, we do the reverse. Our custom spec augment method is designed to make use of the fact that the different events in our data set have different time lengths. So for example, a vacuum cleaner typically has much longer durations than something like dishes. So for each clip, we pick the top 2 events from the labels, and we apply a time mask, which is 0.25 times the median duration of those events. So this gives us a variable length time mask for each clip. And finally, for the loss masking, this is done on the predictions of the model. And the idea is that we want to be able to better train the model, given that these predictions are often very sparse. So there's two types of masking that we experimented with. Event masking, where we set all the events that were not present in the clip to be 0. And segment masking, where we set all the frames that did not contain positive events to be 0, with a 12 millisecond buffer before and after each segment. Our results are shown in the table and are compared with the top submission and the top single model submission from the same team. As you can see, we achieved a similar event-based macro F1 score of 42.7%. And this has improved over a 34.7% performance from vanilla KD. We also find that our custom spec-og procedure got the best results, followed by standard spec-og and no spec-og. And furthermore, event masking achieved the best results, followed by segment masking and then no masking. This suggests that masking definitely helps the student model learn, but doing segment masking might be too aggressive. And for each of these experiments, we ran 10 trials, and we took the validation F1 scores of each of those 10 trials and performed a statistical test by using a 2-sampled independent t-test. The t-tests show that the curriculum learning schemes have a statistically significant effect at the alpha equals 0.2 level, while all the other techniques are significant at the alpha equals 0.05 level. So in conclusion, this paper shows that several new techniques can be used to train a student model, which is a 3-layer LSTM model on an AED task. We use progressively applying pseudo-label sampled, variable length time masking in spec-og, and using event masking the loss function to achieve state-of-the-art performance. So this is the conclusion of our intro video to this paper. Please attend the poster section and ask me any questions, and I hope you enjoy listening to this video. Thank you.